NaN. In computing, NaN, standing for not a number, is a member of a numeric data type that can be interpreted as a value that is undefined or unrepresentable, especially in floating-point arithmetic. Systematic use of NaNs was introduced by the E754 floating-point standard in 1985, along with the representation of other non-finite quantities such as infinities. In mathematics, 0 divided by 0 is undefined and is therefore represented by NaN in computing systems. The square root of a negative number is not a real number and is therefore also represented by NaN in compliant computing systems. NaNs may also be used to represent missing values in computations. Two separate kinds of NaNs are provided, termed quiet NaNs and signaling NaNs. Quiet NaNs are used to propagate errors resulting from invalid operations or values. Signaling NaNs can support advanced features such as mixing numerical and symbolic computation or other extensions to basic floating-point arithmetic. Floating point. In floating-point calculations, NaN is not the same as infinity, although both are typically handled as special cases in floating-point representations of real numbers as well as in floating-point operations. An invalid operation is also not the same as an arithmetic overflow, which might return an infinity, or an arithmetic underflow, which would return the smallest normal number, a subnormal number, or 0. E754 NaNs are encoded with the exponent field filled with ones like infinity values, and some non-zero number in the significant field to make them distinct from infinity values. This allows the definition of multiple distinct NaN values, depending on which bits are set in the significant field, but also on the value of the leading sign. For example, a bitwise E754 single precision 32-bit NaN would be, where S is the sign most often ignored in applications, and the X sequence represents a non-zero number, the value 0 encodes infinities. The most significant bit from X is used to determine the type of NaN, quiet NaN, or signaling NaN. The remaining bits encode a payload most often ignored in applications. Floating-point operations other than ordered comparisons normally propagate a quiet NaN and QNaN. Most floating-point operations on a signaling NaN signal the invalid operation exception. The default exception action is then the same as for QNaN operands, and they produce a QNaN if producing a floating-point result. The propagation of quiet NaNs through arithmetic operations allows errors to be detected at the end of a sequence of operations without extensive testing during intermediate stages. For example, if one starts with a NaN and adds 1 5 times in a row, each addition results in a NaN. But there is no need to check each calculation because one can just note that the final result is NaN. However, depending on the language and the function, NaNs can silently be removed from a chain of calculations where one calculation in the chain would give a constant result for all other floating-point values. For example, the calculation x0 may produce the result 1, even where x is NaN, so checking only the final result would obscure the fact that a calculation before the x0 resulted in a NaN. In general, then, a later test for a set invalid flag is needed to detect all cases where NaNs are introduced. See function definition below for further details. In section 6.2 of the old E754-2008 standard, there are two anomalous functions, the maxnum and minnum functions, which return the maximum and the minimum, respectively, of two operands that are expected to be numbers that favor numbers if just one of the operands is a NaN and then the value of the other operand is returned. The E754-2019 revision has replaced these functions as they are not associative when a signaling NaN appears in an operand. Comparison with NaN. A comparison with a NaN always returns an unordered result, even when comparing with itself. The comparison predicates are either signaling or non-signaling on quiet NaN operands. The signaling versions signal the invalid operation exception for such comparisons. The equality and inequality predicates are non-signaling, so x equals x returning false can be used to test if x is a quiet NaN. The other standard comparison predicates are all signaling if they receive a NaN operand. The standard also provides non-signaling versions of these other predicates. The predicate is not an x determines if a value is a NaN and never signals an exception, even if x is a signaling NaN. Operations generating NaN. There are three kinds of operations that can return NaN. Most operations with at least one NaN operand. Indeterminate forms, the divisions +0/+0 and +/+, the multiplications +0 x plus and +x plus 0, remainder x% y when x is an infinity or y is 0, the additions plus, and equivalent subtractions and, 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 and. The standard has alternative functions for powers. The standard pow function and the integer exponent pound function define 0, 1, and 0 as 1. The power function defines all three indeterminate forms as invalid operations and so returns NaN. Real operations with complex results, for example, the square root of a negative number, a logarithm of a negative number, the inverse sine or inverse cosine of a number that is less than 1 or greater than 1. NaNs may also be explicitly assigned to variables, typically as a representation for missing values. Prior to the E standard, programmers often used a special value such as 99,999,999 to represent undefined or missing values, but there was no guarantee that they would be handled consistently or correctly. NaNs are not necessarily generated in all the above cases. If an operation can produce an exception condition and traps are not masked, then the operation will cause a trap instead. If an operand is a quiet NaN, and there is also no signaling NaN operand, then there is no exception condition, and the result is a quiet NaN. Explicit assignments will not cause an exception, even for signaling NaNs. Quiet NaN, quiet NaNs, or QNaNs, do not raise any additional exceptions as they propagate through most operations. The exceptions are where the NaN cannot simply be passed through unchanged to the output, such as in format conversions or certain comparison operations. Signaling NaN. Signaling NaNs or SNaNs are special forms of a NaN that, when consumed by most operations, should raise the invalid operation exception and then, if appropriate, be quieted into a QNaN that may then propagate. They were introduced in E754. There have been several ideas for how these might be used. Filling uninitialized memory with signaling NaNs would produce the invalid operation exception if the data is used before it is initialized. Using an SNaN as a placeholder for a more complicated object, such as a representation of a number that has underflowed, a representation of a number that has overflowed, number in a higher precision format, a complex number when encountered. A trap handler could decode the SNaN and return an index to the computed result. In practice, this approach is faced with many complications. The treatment of the sign bit of NaNs for some simple operations, such as absolute value, is different from that for arithmetic operations. Traps are not required by the standard. There are other approaches to this sort of problem that would be more portable. Payload operations. E754-2019 recommends the operations get payload, and set payload signaling be implemented, standardizing the access to payloads to streamline application use. According to the E754-2019 background document, this recommendation should be interpreted as required for new implementations, with reservation for backward compatibility. Function definition. There are differences of opinion about the proper definition for the result of a numeric function that receives a quiet NaN as input. One view is that the NaN should propagate to the output of the function in all cases to propagate the indication of an error. Another view, and the one taken by the ISO C99 and E754-2008 standards in general, is that if the function has multiple arguments and the output is uniquely determined by all the non-NaN inputs including infinity, thus, for example, the value returned by hypat plus q0n and hypat non plus is plus. The problem is particularly acute for the exponentiation function PAUX, y equals xy. The expressions 0, 0, and 1 are considered indeterminate forms when they occur as limits just like x0, and the question of whether 0 to the 0 power should be defined as 1 has divided opinion. If the output is considered as undefined when a parameter is undefined, then POUN q0n should produce a q0n. However, math libraries have typically returned 1 for POUN, y for any real number y, and even when y is an infinity. Similarly, they produce 1 for PAUX, 0 even when x is 0 or an infinity. The rationale for returning the value 1 for the indeterminate forms was that the value of functions at singular points can be taken as a particular value if that value is in the limit the value for all but a vanishingly small par. The 2008 version of the E754 standard says that POUN, q0n and PAUC0n, 0 should both return 1 since they return 1 whatever else is used instead of quiet NaN. Moreover, ISO C99 and later E754-2008 chose to specify POU1 plus equals 1 instead of q0n. The reason of this choice is given in the C rationale. Generally, C99 eschews a NaN result where a numerical value is useful. The result of POU2. To satisfy those wishing a more strict interpretation of how the power function should act, the 2008 standard defines 2 additional power functions, PAUX n, where the exponent must be an integer, and PAUX y, which returns a NaN whenever a parameter is a NaN or the exponentiation would give an indeterminate form. Integer NaN. Most fixed-size integer formats cannot explicitly indicate invalid data. In such a case, when converting NaN to an integer type, the E754 standard requires that an invalid operation exception be signaled. For example, in Java, such operations throw instances of Java arithmetic exception. In C, they lead to undefined behavior, but if Annex F is supported, the operation yields an invalid floating point exception as required by the E standard and an unspecified value. Perl's math big int package uses NaN for the result of strings that do not represent valid integers. Display, 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 display. Different operating systems and programming languages may have different string representations of NaN. NaN C, C++ output, NaN ECMAScript, Rusts, Rusts, Rusts script, Rusts, Rusts, Rusts script, Rust, Rusts, 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 NaN %, NaN Rust, C, C++ source code, NaN Q IBM Excel and AIX Fortran, C++ proposal in 2290. NaN S ditto, Q NaN, S NaN, 1, hash NaN Excel, and Excel, 1, hash Q NaN Excel, -1, hash IND Excel, plus NaN 0 scheme. Since in practice encoded NaNs have a sign, a quiet slash signaling bit, and optional diagnostic information sometimes called a payload, these will occasionally be found in string representations of NaNs. 2. Some examples are, for the C and C++ languages, The sign bit is always shown by the standard library functions, e.g. NaN, when present. There is no standard display of the payload nor of the signaling status, but a quiet NaN and value of a specific payload may either be constructed by providing the string NaN sequence to a number parsing function. GCC and LLVM provides built-in implementations of NaN and NaNs. They parse the char sequence as an integer for str_tal or a differently sized equivalent with its detection of integer bases. The GNUC library's float parser uses the char sequence string in some unspecified fashion. In practice, this parsing has been equivalent to GCC/LLVMs for up to 64 bits of payload. NuLib does not implement NaN parsing, but strtod accepts a hexadecimal format without prefix. Muscle does not implement any payload parsing. Not all languages admit the existence of multiple NaNs. For example, ECMAScript only uses one NaN value throughout. Encoding. In E754 standard conforming floating point storage formats, NaNs are identified by specific, predefined bit patterns unique to NaNs. The sign bit does not matter. Binary format NaNs are represented with the exponential field filled with ones like infinity values and some non-zero number in the significant field to make them distinct from infinity values. The original E754 standard from 1985 E754-1985 only described binary floating point formats and did not specify how the signaling/quiet state was to be tagged. In practice, the most significant bit of the significant field determined whether a NaN is signaling or quiet. Two different implementations with reversed meanings resulted. Most processors, including those of the Intel and AMD's 86 family, the Motorola 68000 family, the AIM PowerPC family, the ARM family, the SunSpark family, and optionally new MIPS processors set the signaling/quiet bit to non-zero if the NaN is quiet, and to 0 if the NaN is signaling. Thus, on these processors, the bit represents an is-quiet flag. In NaNs generated by the PA RISC and old MIPS processors, the signaling/quiet bit is 0 if the NaN is quiet and non-zero if the NaN is signaling. Thus, on these processors, the bit represents an is signaling flag. The former choice has been preferred as it allows the implementation to quiet a signaling NaN by just setting the signaling/quiet bit to 1. The reverse is not possible with the latter choice because setting the signaling/quiet bit to 0 could yield an infinity. The 2008 and 2019 revisions of the E754 standard make formal requirements and recommendations for the encoding of the signaling/quiet state. For binary interchange formats, the most significant bit of the significant field is exclusively used to distinguish between quiet and signaling NaNs. Moreover, it should be an is-quiet flag. That is, this bit is non-zero if the NaN is quiet and 0 if the NaN is signaling. For decimal interchange formats, whether binary or decimal encoded, a NaN is identified by having the top 5 bits of the combination field after the sign bit set to ones. The 6th bit of the field is the is signaling flag. That is, this bit is 0 if the NaN is quiet and non-zero if the NaN is signaling. For E754-2008 conformance, the meaning of the signaling/quiet bit in recent MIPS processors is now configurable via the NaN 2008 field of the SCSR register. This support is optional in MIPS Release 3 and required in Release 5. The state/value of the remaining bits of the significant field are not defined by the standard. This value is called the payload of the NaN. If an operation has a single NaN input and propagates it to the output, the result NaN's payload should be that of the input NaN, and this is not always possible for binary formats when the signaling/quiet state is encoded by an is signaling flag, as explained above. If there are multiple NaN inputs, the result NaN's payload should be from one of the input NaNs. The standard does not specify which.